So I am presenting on how I solved for the tension that was required uh, for this book to fall down, and also I also ended up calculating for the torque that was put on the book for it to fall down. So what gives it tension is this cup. So as I add water, the weight of the cup increases, and which increases the tension on this string, which once the book falls, this is the tension is finally let go, and the cup, all that force that was on the string is now on the water. It displaces more water, which gives it more buoyant force. That's why it remains pretty much in the same place. It just sinks a little once the tension leaves the system. So I said that I added around 125 milliliters of water for the book to fall down. So right now it doesn't have much tension, it's just there. But once I add water, the book falls. Now, knowing what our system looks like, what do we need to solve for tension? Really, we only need the amount of water that I put in, and then I can solve for the mass of the water by using density. So density of water is around 1 gram per milliliter, and I have the milliliters of water, which I got using the measuring cup. And that's also how I got all my errors from the tools that I used, and then I used those errors to calculate for uncertainties. So we know that the tension of the string on the cup goes straight up because of how it's placed on the other cup, and then it sort of does this pulley thing where it like goes like this and then over here at an angle. But that doesn't really matter for like knowing how much tension the cup applies on the rope. It won't so knowing that, our free body diagrams will look like where the force of buoyancy is up and the force of tension is up, and then the force of the weight is down, and the force of the weight is equal to the force of the buoyancy plus the force of the tension. Now when we add before we added water, there was like just about no tension, but once we added water, the tension increased and the force of buoyancy stayed about the same because the cup didn't move. So knowing that, we just need to calculate for how much mass of water there is, which I explained. I used P equals M divided by V, M being the mass, V equal being the volume, P being the density of water. And so I got the mass. I solved for uncertainty using the error in the precision of my measuring cup. Then once I got the mass, I know that the weight of the water is equal to the tension. The weight of the water added is equal to the tension on the cup. So I just calculate the weight of the water, which is gravity times the mass of the water, and then I calculated the uncertainty of that using the uncertainty I got before, but the uncertainty I got before for the mass of the water, and I didn't use any uncertainty for gravity. I assumed there was zero uncertainty. And then we can go a step further and calculate for the what's it called? The torque on the system. So we use the angle of that the string is pulling from we use the angle that the string is pulling the book from, so that is equal to 60 degrees, and I got that with a tool that I used to measure. And then I use the uncertainty from the tool to as the I use the precision of the tool as the uncertainty, and then I to find torque, it was just the height of the book, which I measured with a ruler, which I also got the uncertainty from the precision of the ruler, and so it's torque equals height times tension times sine theta of that angle, which it was 60 degrees. So I solve for the torque, and then I solved for the uncertainty using the uncertainty of the angle, the height, and the tension. And yeah, that's torque, and super fun. So let me just show you my values. It was for torque, I got 0.229 plus or minus 0.027 Newton meters. So it's not a lot of torque in there. And then for the tension, the force of tension is I got 1.23 plus or minus 0.13 newtons.